So today we're gonna dig deeper into amplifier, and if you are curious where it is on the textbook, it's gonna be in the, section 6.2. So for amplifier, you can treat it like a black box. So the electronic circuit in here is a black box for your amplifier. There's two things. Okay, first is you have to power it. Okay, so you have to connect your amplifier to a power supply and ground it properly. Then you give it an input and output. Input is usually the small signal or some kind of signal that you want to amplify, and the output is your post amplify signal. So the goal of this lecture is first to investigate the process by which the simple transistor circuit can amplify a small time varying input signal, and the second goal is to derive a small signal model of the transistor. Okay, so what type of amplifier circuit that we saw before? So I just give you two in here. So in the left circuit, the input signal is Vi, and it contains both basically DC and AC signal. And basically this is a bipolar transistor inverter circuit without bias, because here is the source itself. However, in this right circuit here, this is the more appropriate way to amplify your signal, because in here you have VBB is the DC voltage that bias the transistor to a particular Q point, and your small signal Vs is the AC signal that you want to amplify. Then you can get the output right here in VO. So in here you have the voltage transfer characteristic of the second circuit, or the inverter amplifier with bias. Okay, in here you can see that the transistor need to be biased with an appropriate DC voltage at Q point. Okay, so if you do that, then you are able to appropriately use this circuit as an amplifier. Like previously discussed, if you over bias it to this point, it's gonna show some cutoff characteristic, or if you under bias it in this point, yeah, you can see other cutoff characteristic. So what you want to do is figure out the appropriate Q point and bias your circuit properly. So in this chapter, we will have to go through both AC and DC condition. That means both DC and time varying conditions. So let's go through some of the notation so that we can be clear to move on in the next step. So first of all, you can see that of course I will represent for current, B represent for voltage, but B stand for base, E stand for collector, and BE stand for base collector junction. BE stand for base emitter junction. So we have both uppercase I and uppercase lowercase I. We have also uppercase and lowercase for B, and uppercase and lowercase for B and BE. So for example, if you see the I and B in lowercase and the subscript, for example, base or collector, if the current and voltage in lowercase and subscript in uppercase, that means it is the total instantaneous value. Okay, that means it is the value at a certain time, the value of the signal at a certain time. When everything is uppercase, including the current voltage and the subscript, you are talking about the DC values. However, if you have I is small, like IB in lowercase, and BE is in upper is also in lowercase, you are talking about the instantaneous AC values, okay, AC value. And finally, if you have uppercase B, uppercase B, uppercase I, uppercase B, but the subscript is in lowercase, you are talking about the phasors value. So on the right side here, you have the circuit with the inverter amplifier circuit with the bias voltage and the small signal that you need to amplify. On the right side is your transistor characteristic with a DC load line, a Q point, and the sinusoidal signal source versus the sinusoidal signal source, which is here, and that would be Vs. Okay, so if Vs vary, your base current will vary, and basically this line here will vary up and down a little bit. So if you can use that, well, you can use your load line here based on the quenching base or your Q point. Then you can figure out what is the response, the sinusoidal response for your collector emitter voltage and also your collector current. So technically, the time varying current corresponds by the small signal Vs at the base. It induces an AC collector current that superimposes on the quenching collector current. The AC collector current then produces a time varying voltage across the RC, which is the collector resistance, which then induces an AC collector emitter voltage as shown in this figure. The AC collector emitter voltage or the output voltage in general will be larger than the sinusoidal input signal, so that the circuit has produced signal amplification. That is, the circuit is an amplifier. Okay, so this is the the exponential growth that I was talking about to you guys previously. So if you see in here, if you increase VBE, then IB will grow exponentially, and that is because of this relationship in here. And VT is the thermal voltage, okay, so it's depending on K and E are constant and T is just temperature. So if you are operating this at RT, then you can estimate that to be 0.026 volt or 26 millivolt. Okay, so what is the goal here, and why are we calling this one small signal mathematical model? So if you see exponential growth, it's difficult to analyze, difficult to predict, right? If you want to build an amplifier, you want the growth relationship to be linear. However, this is exponential. So what you can do is, okay, if you don't need to amplify a large variation of signal, if the signal variation is very small, so if the peak to peak or the amplitude of this signal is small enough, what you can do is you can cut this curve into a small section. Then you can use linear estimation to smoothen it out and assume this section to be linear. Then you can try to have a relationship between IB and VE, which is linear. So the goal of this slide will be trying to figure out how to express IB in a linear relationship to VBE. Okay, so let's go. So if VBE is composed with a DC term with a sinusoidal component superimposed, so for example, VE can be, this is the DC term, VBEQ, okay, then the sinusoidal superimposed component will be the small v here, small VBE. Okay, so that is our VBE, like V is going to be large. So if we do that, we can plug this one in here. Okay, so we plug this one in here. We have this equation here. Then you know it's exponential. So if you have exponential a plus b equal, that will be equal to exponential a multiplied by exponential b. Okay, so you write again like this. You have this term is actually is your IBQ. Okay, so you can write your equation again and replace this whole thing with IBQ. That's a lot better, but it's still not linear. Like, what are we doing? Okay, so the secret is here. You can use Taylor series. Okay, and when you use the Taylor series, you apply the Taylor series, you keep only the linear term, and this approximation of Taylor series is why this model is going to be called small signal. So, okay, so you use Taylor series, approximate this exponential terms. Okay, so only go with the first couple terms, so that keep it linear. Then you finish the math, then you will have the basically your linear relationship between IB and VBE. Okay, you can also write it again like, okay, with the IB small b, and basically IB is technically just this whole group here, like IB equal IBQ over VT multiplied by VBE. But in summary, you can do it. You can express IB in terms of a linear relationship to VBE. Okay. So in this case, the term small signal refers to the condition in which VBE, this one, is sufficiently small for the linear relationship between IB and VBE, okay, given by this equation to be valid. As a general rule of thumb, okay, if VBE is less than 10 millivolt, the exponential relation given by this equation, okay, that so that estimation will be approximately correct within 10%. So ensuring this voltage less than 10 millivolt is another useful rule of thumb in designing a linear bipolar transistor amplifier. If VBE signal is assumed to be sinusoidal, but if the magnitude becomes too large, then the output signal will no longer be pure sinusoidal voltage, but will become distorted and contain harmonic. So next we move to AC equivalent circuit. So we started with the standard circuit that we have in here. Given our signal are basically our signal are a small AC signal superimposed on the DC value, so we can break it down into two. So each the current, for example, the base current, collector current, collector emitter voltage, and base emitter voltage. Each of them actually have two different. Component. One is the AC component and the other one is the DC component. So first, let's consider the base emitter loop, which is this loop. So the first scenario is when this signal source is turned off, Vs equals 0. Okay, So in that scenario, you do the K-curve voltage lower. You can write down this equation here when the base bias voltage, the VBB equal IBQ multiplied by RB plus VBEQ. But when you turn on this the signal source, so Vs will be different than 0. Okay, now you're adding a few more terms. On the base, you're adding Vs, okay, which is the signal source. In the base current, you add in the AC term of the base current. So you plug in the whole full term here, and in the VBE terms, you want to plug in the whole things here. Okay, that includes the DC portion and the AC portion of your signal. Okay, so now you want to do some magical arrangement. Okay, so what you want to do is, you see I put some notation in red, right? So you want to move all the blue terms into one side and all the red term into one side. Okay, so now you try to apply this equation into these terms, then you can have this whole terms equal to 0. Okay, why? Because technically you just have to move this two thing over here, then you can have VBB minus this two thing equal 0. So you can get rid of this two term here. Then you have this equation. Okay. So once again, we're gonna do the same thing on the collector emitter loop. So this loop right here. Okay. So we consider two scenarios. First is when Vs equals 0. So if Vs equals 0, then we have this equation here. Pretty easy. You just basically you go through the K-curve, voltage lower over this loop. But then when you turn on Vs is different from 0. And now you add in one of the, how can I say this, the AC component of the collector current and the collector emitter voltage. So you add in a small IC and a small VC. Okay, same way you do the magical arrangement. Okay, you put all of the DC on one side, AC on one side, and the DC component you can make it to 0. Okay, and finally you have this equation. VC equal negative IC multiplied by RC. So the main thing that the result from that two analysis is that so when you work with the base emitter loop, you have an equation that relating the AC signal voltage, the AC component of base current, the base emitter voltage. When you work with the collector emitter loop, you have the AC component of collector emitter voltage, then the AC portion of the collector current. So you have all of the equation that relate all of the AC parameter of your circuit. Therefore, now you can construct your AC equivalent circuit. So all of the currents and voltages show our time varying signal in this equivalent circuit here. We should stress that this circuit is an equivalent circuit. They are implicitly assuming that the transistor is still biased in the forward active region with appropriate DC voltage and currents. One thing to notice is in this AC equivalent circuit, you technically get rid of all of the supply power. You don't have VCC and VBB anymore because you already established the equivalent signal for it. Okay, that's it for today. Next, I will try to go over hybrid pi model. There's a note on H parameter I have put on Canvas, so please take a look on it. In the meantime, we will cover hybrid pi model, and later on I will discuss about that note. Thank you very much.